Hey, welcome to the Art of Code. My name is Martijn and this is part 2 of the Conway's Game of Life video. If you haven't checked out part 1, be sure to check that out. The link is in the description. Alright, so let's get started. So in this video I thought to just try to make this a little bit cooler than what it is right now. So in the last video we made the actual life algorithm itself. And so now let's see what we can do to make this a little bit better. So the first thing I want to do is so I don't have to reset this every time after it dies. Is I want to be able to draw into this with the mouse, and that is pretty simple. What I can do is I go to buffer A here. And basically what we have to say is that, okay, we do life, but regardless of whatever happens here, we also put some pixels alive where the mouse is. Okay, so, well, that is fairly simple, because what I can do is I can say if the distance between the mouse .xy and the frag chord, the pixel coordinate, .xy, if that is smaller than, let's say, 2 pixels, then make the color or make the cell alive. And the way to do that is just by saying just put all of the values to 1. Okay, so now you can see that I can draw stuff inside of here. It's just that that dot stays there even though, well, it's a bit small. Let me just make it bigger. So let's say 20. It's just that the dot is also there when I'm not clicking. Well, that's easy enough. I can just say if iMouse.z is bigger than 0.5 and the distance blah blah blah. And that just makes it that only when I click, we'll have to recompile, that only when I click it does that. If I don't click, it's gone. And I did distance here, okay, like, so distance is one way to do it. Like generally, the distance between 2 vectors, I like to write it like this. It's the length of the vector of, it's the length of the difference of vectors. Okay, that's the same thing, basically. All right, so that is one thing. Let's just have a look at that real quick. So now I can draw here a bunch of stuff, which is pretty neat. Okay, the next thing I want to do is I want to make sure that, I want to make it so that we see this a little bit bigger, because right now it goes on the pixel scale, and that's all cool, but you can't really see that much. So let's zoom into this. So for that, I will still simulate life on a per pixel level, but I will just display something else. So instead of displaying the entire texture, I can just display a smaller part of the texture by just multiplying this UV coordinate. So this UV coordinate goes from 0 to 1 right now, meaning that it displays the entire texture. But if I multiply this by, say, 0.5, then it only displays half of the texture. Okay, so now two things. Well, the first thing is that now it looks soft. It doesn't look hard pixely anymore, and that is because of texture filtering. I said before that this thing filters the texture when it gets blown up or it gets made smaller, and for most purposes inside of video games, that is what you want, because you don't want stuff to look pixely when you get close up to it. But in this case, we kind of do want that. So what I'm going to do here is I'm going to go into sampler options. I'm going to set this from linear to nearest. And that just makes it that my pixels stay hard edged. Okay, so that was one thing. So that's already pretty cool. So we can zoom in even farther like this. But now the drawing broke, you see, because like now I can't draw anymore in here. And actually I can draw. If I go over here, you see I draw. But over here, like the brush doesn't stick to my cursor anymore. And that is because this value over here, we also need to compensate for that over here inside of the mouse there. So over here we'd have to say the same thing in order to make sure that we're still in the same spot. And it's never in programming a good idea to have one value hard-coded in multiple places. So if you have anything that is used in multiple places and that's supposed to stay in sync, then you should make it one value instead of having multiple values. Luckily, inside of ShaderToy, we can do that because we can make another tab, a special tab named Common. And the Common tab is, like it says on the box, it is whatever you define here is what is available to all of the other tabs. So here I can make a define, and I call it size. And then I can say size equals 10, let's say. And then what I do over here, instead of multiplying it, I divide it by that. So divide by size, and then similarly over here I will divide it by size. So that now I have a size and I can still draw. Doesn't matter what size it is, it will always work properly. So let's also take this out here. So we'll call this brush size, and let's also stick that in the beginning, so, or in the Common tab. So define brush size, and the brush size is in pixels. And so if we want the smallest brush, I think we can do this. Maybe we can make it even smaller because it makes a circle with the radius of this, right? So this would already be 2 pixels that it makes it. So it doesn't actually draw 1 pixel. So let me see if I can make it smaller. I'm not sure if that's going to work. Yeah, okay, so that draws one pixel. It's just that 1 pixel on its own will die right away, so that doesn't really help. So for now, let's just set it to 1 so that at least we have a bunch of pixels so we can actually draw some activity. Okay, now the next problem is that this goes too fast. Like, you can't really appreciate what's happening right now because it does 60 time steps per second. So everything goes really fast. And while that is nice, perhaps if you're looking at something like this, but if you're zoomed in, you kind of want time to go slower. And so for that, what we're going to do is we're going to go here to buffer A, where we have this thing. And so here we're saying, okay, we're initializing for the first 100 frames. Actually, let's just put it back to 10 frames. For the first 10 frames, we're going to do that, and then afterwards, every frame we're going to do a simulation step, right? We're going to do a life step. But we don't have to do that. Like, what we can do is we can say, well, only do that every nth step, every second step, every fifth step, every 10th step, or whatever. And the way to do that is, like, inside of here, I can do else if IFrame. I can do a modulo operation on IFrame. So IFrame is an integer that goes from 0, 1, 2, 3, whatever. It increases like 1 frame every time. And I can do a modulo on that. I can say, okay, if the modulo is basically the remainder after a division, right? So basically what this does, the percentage character here, is it divides IFrame by 10 and it gives you back the remainder after that. And so the remainder of that is going to be it's going to be 0 for every multiple of 10, right? Like if IFrame equals 5 and you divide by 10, well, then the remainder is 5. If IFrame equals 10 and you divide by 10, the remainder equals 0. If IFrame is 12 and you divide by 10, the remainder equals 2. So every multiple of 10, the remainder is going to be 0. And so if I say this, so this only happens once every 10 frames. Okay. Now so here, once every 10 frames, I want to do this life, and then otherwise I just want to read from the texture directly. And so what I'm going to do here is I'm just going to invert this. So I'm going to say, so this happens once every 10 frames. If I invert this like that, then that happens most of the time, and once every 10 frames it actually goes into do life. But for all the other frames it goes here. And so here what I can do is I can just say, well, just display the texture without any simulation step. So the texture is buffer A, which is an iChannel 1, UV. So let's see what that does. Okay, so now it only does that update step once every 10 frames, so it goes a lot slower. And so now we can make it as slow as we want. We can have it once every 20 frames. So now, like, supposedly that only goes 3 times a second. It does an update step, which makes stuff a lot easier to understand or to appreciate what's going on, which is pretty cool. So let's see here. Let's destroy some still lifes. Okay, that is pretty cool. Now the next thing I would like to do is perhaps we don't want to just have a simple pixel display here. Perhaps we want, instead of little pixels, we want like little dots to represent a live cell as opposed to a fully fledged pixel. And so for that, let me just first zoom in a little bit to make it even bigger. Okay, so this buffer A holds the information of the life field, and then the image just renders that field, right? And so what we want to do is we want to change the rendering. Like the underlying data stays the same, but we're rendering it in a different way. And for that, I can go over here and, well, let's just first draw a bunch of circles for each of these pixels. So for that, what I can do is I make a grid UV, GV, and that's gonna be the fract of the UV. So if I do this, the fract of UV times some larger value, and then minus 0.5. So basically this, so normally my UV coordinate goes from 0 to 1. If I multiply it, it goes from 0 to 10. If I take the fractional component of that, then basically it's the remainder each time, or it's the decimal component each time. So it will go from 0 to 1, 0, 1, 0, 1, 0, 1, all the way 10 times, right? So what comes out of this is a value that goes from 0 to 1, but I want it to go from minus 0.5 to 0.5, so I'm going to subtract that from it. And now I can calculate the distance from like this coordinate to the center of each box. So basically this makes boxes, right? So let me just visualize the boxes that it makes. I could just do like that. Let's say, okay, so there is a bunch of boxes, and they're not square because this isn't normalized. But that's not the end of the world. And obviously we want those boxes to be coinciding with where the pixels are. So for that, we're going to have to use frag coord, because we did this in pixel coordinates, not in normalized coordinates. So I'm going to get the pixel coordinates here by taking frag coord, and then I'm going to have to divide that by size as well. So let's see what that does. Okay, so that gives me boxes that are exactly the same size as our pixels. Okay, and now what I can do, I can use that coordinate to draw a little circle. And actually, let me just make it even larger because it's better for everybody to see. Okay, so we have a bunch of boxes, and now inside of each box we can just draw a pixel. Sorry, we can just draw a circle. So what I'm going to do here is I'm going to calculate first. In order to draw a circle, you need to know what the distance is to the center of the circle. Basically, a circle is defined as, or a disk I should say. A disk is defined as every point that is less than the radius away from the center of that disk, right? So what I can do for that is I can just get the length of GV, because the center of my disk at 0, 0, right? I want the center of the disk to be in the middle of each box. Let me just draw some more here. Or maybe just reset. So this gets me the distance from any pixel to the center of its current box, and then I can use a smooth step to cut out a circle. So I can say call, let's say plus equals smooth step of D, and then well, it depends on whether I want a hard circle or a soft circle. Let's do a hard circle minus. Well, here, let me just do it first like this. 0.5, 0.4, let's say. Okay, so that makes circles everywhere. And if you don't know how this works, I made videos about this before. If you don't know how smooth step works, go check out my video specifically about smooth step. I have a whole video about that. Or go check out Shader Toy for absolute beginners to know how I drew this circle just now. But I'm gonna do it slightly different. So what I can do is, instead of having these larger, I can just subtract that from here. Subtract the radius from here. Let's say I want the circle of a radius of 0.3, and then I want the edge to be 0.1 wide. Like, so it's a little bit smooth, right? If I make this smaller, it's going to be a sharper circle. But let's say I want it like this. And then I'm going to make this a little bit larger still. Yeah, something like that. Okay, so now I want that, like, in order to have the live pixels be a circle and the dead pixels nothing, I can just multiply those two together. And then also get rid of the coloration. And look at that. So now we have a bunch of circles instead of pixels, which looks much nicer. So let's have a little break and let's have a look at what you guys made. One of my last tutorials was a American flag for the 4th of July, and I asked you guys that if you make something, to share it with me so that I could add it to the next video. So that's what I'm doing right now. We got a bunch of flags from all over the world. Thank you very much, Art of Code family. That's really, really cool. So yeah, this was the flag that I started with. And yeah, here we get all the other flags, so enjoy. Aggie42 actually made 3 different flags from all kinds of tropical destinations that I had no clue what their flag looked like, and now I do, so that's awesome. We got Africa represent, India represented multiple times. China, of course, Malaysia, Korea. I did not know that those patterns are different all over the place, from left to right on the Korean flag. There was Brazil, Macedonia, no idea that the flag looked like that. Obviously a Union Jack. And one shape made this. How cool is that? Alright, so let's get back to life. Alright, so now to end, let's do one more thing. Let's add a trail to this so that we can see how this evolved over time. And to do that, let's see here, what would be the best way to do this? I think I'm going to add another buffer. So I'm going to go click here, buffer B. And buffer B is going to take buffer A, which is the current information, right? So buffer A. I'm going to take buffer A, and then I'm going to do some stuff to it. And let's see, how can I do that? I'm just basically going to make that buffer B takes itself, or it renders to itself, and it will attenuate itself at each step. Anyways, like let me just do it, and we'll see how it works. Vec for old, which is all the old frames that we want to kind of slowly fade away. And old is, I'm going to read that from myself, which is, I'm in buffer B right now, so I'm going to read that from buffer B. So I'm going to make a buffer B over here. So I channel 1, and with a UV coordinate that I'm going to have to again create over here. Control C and like that. So that is my old trails and whatnot, and the new one is just channel 0, right? Because the current one is always in A. So that's the new one. New. And now I'm just going to mix the old and the new together. I can just do that right here directly. So I can say mix old and new, and then with some value. And if that value is 0, the way mix works is that 0 will just return the first value, 1 will return the second value, and anywhere in between 0 and 1 it will linearly interpolate between those values. And so if I want this to be to leave a trail, then every time I render this, I should be mostly rendering the old one. Do I have that right? I'm not sure. Hang on a second. So let me just try this. And so now over here, instead of getting the new version, I get the trail version. Actually, let me just add the trail version over here. And say that. Let's see what that does. Oh, and also what I need to always do is make sure that this is set to nearest, so that I don't get any interpolation that doesn't work proper. All right. Yeah, so I guess that worked. Let me see if I cannot make this a little bit nicer. Let's make this smaller. 0.2, let's say. Okay, and now I probably have to zoom out a little bit in order to be able to see this properly. So let's go back to here, and also let's play it faster. And another thing, by the way, for this, let's just take this out and make that its own thing. What do I call this? Speed, I guess. Although it's the inverse of speed, but anyways. So define speed 20. Yeah, although I don't really like that, because now it's kind of the inverse, right? Because the smaller speed is, the faster it goes. Anyways, I'll leave that as an exercise to you to make that so that it goes faster if the number is bigger. How would you do that? Leave a comment down below. All right, so now let's see here. Yeah, okay, so now we're just seeing the history, but we don't see the actual. Oh, this looks interesting though. So there's all these kind of happy accidents that can sometimes be pretty cool. Let's see here. I'm doing this all off the top of my head, so I'm probably not doing something right. Let me just do something else. So instead of this here, let's say we take the maximum between the old and the new. So maximum between the old and the new. And then for the old, we're going to attenuate it a little bit. And the way to attenuate is by multiplying by a number that is smaller than 1. So let's see what that does. So that looks already better. Yeah, I think this is better. So now this number, the closer it is to 1, the longer your trails are. So if I make this like 98, then you see it goes very, very slow. It disappears very, very slowly, the trail. Let me see here. It would be nice if I got a glider so you can actually see. Yeah, I guess on gliders you can see that it has a trail, right? So yeah, so you can play around with this and make many cool things. So some things to think about that you could play with is, for instance, well, this rule, right? Like the main rule here. Oh, by the way, before I say that, this can be obviously made a lot smaller. Let's just try to make this smaller here for 1 minute. Just as a fun exercise. So yeah, let me just copy this so that if I screw it up, I still have the old version. So let me just do that. All right. So first of all, we don't need this, right? Because that's already over here. So we can take that out. So that should be fine. Yeah, that still does the same thing. And let me just turn the trail off for now because it's harder to see what we're doing. Okay, so there's that. And then surely we must be able to make this smaller. So if something is alive, n numbers 2 or numbers 3. I think if something is alive, because if numbers equals 3, then it doesn't matter whether you're dead or alive, then the next generation is going to be alive anyway. So I think we can do this like this. If num equals 2, or if alive and num equals 2, or num equals 3, well, that's when you need to be alive, otherwise you need to be dead. I think this does the same thing, but let's just see what that does. Okay, so that does exactly the same thing, and if you want to make it even shorter, you could do this. Can I do that? Yeah, I guess so. We could just do this and make it an inline ternary operator situation, where we say, like, if this is true, then return 1. Oh, sorry. Then return 1, otherwise return 0. I mean, this kind of optimization, the compiler probably takes care of that for you anyway, so really, like, you don't really need to do it, but sometimes it's fun to kind of play around with this and see how small you can get things, you know? And so yeah, so that's how you get that a little bit smaller. Okay, so what was I talking about before? Oh yeah, so that you can play with the rules of this, right? So so I could have played with these rules. So you could say, well, if number equals whatever, what happens if you say number equals 4? What happens then? You know, you get different kinds of shapes, and it's not nearly as interesting because John Conway, the person who invented this in the 70s, before there were computers to do this, by the way, he had to do that with pen and paper to figure out what was the nicest thing, and he came up with this. So yeah, that's why I'm going to stick it there. Basically, it looks like with these kinds of things, they're most interesting when you're right on the border of chaos, right? Because when you're on one side of chaos, like you know, everything will be alive. When you're on the other side of chaos, everything will be dead. And when you're right at the edge of things, it's maybe a metaphor for life, you know, maybe you want to be right at the edge of whatever it is you're doing to have the most interesting outcomes. Anyways, that's a little bit of a philosophical detour. Actually, now that we're on a topic of philosophy, so this is called the game of life, and it's kind of interesting in multiple ways. Like to me, that yeah, it kind of looks like it's alive, but also the fact that this is extremely simple rules that come up with really complicated results, right? We saw before in the first video that you could make this into a computer and you can basically do anything you want with it. And all you need is just an ungodly amount of cells and an ungodly amount of time, and it can do anything. And yeah, like the similarities I see to life is that like life is very complicated if you look at it on our level, but if you go all the way down to, let's say, the atomic level, then it's a lot. I mean, it's still complicated, but it's a lot easier, right? And a lot of people think that because it seems like the smaller in scale you go, like the more easy things get, or the more simple things get, and some armchair philosophers like me, philosophers, would think that, okay, maybe if you go all the way down to, let's say, all the way to the Planck scale, then maybe some similar process to what we're seeing here is going on, and all the complexity that we see is just a result of ungodly amounts of tiny cells that do very simple things, and that's something interesting to think about. So yeah, so let me just make this a little bit bigger. Oh no, actually, man, I talk too much. So yeah, so like one thing you could do is play around with the neighborhood, right? So right now the neighborhood is 1 by 1, or it's 3 by 3. So it goes 1 in each direction. But you can screw around with that. You can, let's say, for instance, we add just 1 pixel in the end that we sample from far away, let's say. So we could sample a pixel based on the number of neighbors that we already had. So if you had three neighbors, then we sample 3 away from the center, or if we had like 5 neighbors, then 5 away from the center. And so let's see what that does. Okay, so that gives me something else here. Let me zoom out. So that gives me a different type of effect, right? And all of these things, they make different types of effects, and it's a lot of fun to kind of play with and see if you can come up with like an interesting result. Okay, so right now I can't really find one. Before I had something that turned really interesting, but anyways, I'll leave it up to you. But you can play with these. You can play with these rules and come up with any kind of result. So Conway's life is an example of a 2D cellular automaton, and a cellular automaton is basically just you have a grid, and every grid cell can determine based on its environment what the next step is. And it doesn't have to be, well, in the case of life, it's either dead or alive. There's only 2 states, but there are other cellular automata where that's not the case, and you can get really cool different looking effects. So so perhaps maybe in the future I will do a video about that. Let me just turn this a little bit slower again, and perhaps a little bit bigger, and then sit back and call this the end of the video. So if you made it all this far, congrats, and thank you so much for following me. And as always, if you make something cool, please share it and comment it below, and either way, I will see you next time.